been really nice. I like the fact that I have a mentor who can like kind of lead me in the right direction, but like not take control of the whole thing. Like it's still me doing all the work and the research. He's just like there to put me on the right path. So I enjoy that, and if actually feels like I'm doing some real research that could help in doing something in the future, we wanted to see like the difference between like the type of airfoils and wings we were using for like smaller aircrafts and drones, not like the commercial planes like the Boeings and all that, because like those are just like really big planes. We were using like basic physics methods, like just like calculating lift, drag, pressure, velocity, and like angle of attack on each of the airfoils, like see which ones help the most. So to start off with, right now in the first week we were just like defining the main fundamental forces, which is like lift, drag, and then thrust and weight. So lift and drag are like they lift is it like lift and weight are the forces that are like opposite each other, and they're like in the y-axis. If you think about it, like it's in a 2D graph, they're like the top and bottom. That's what they affect. And drag and thrust do are opposites of each other and affect the x-axis. We just want to understand how lift is generated, how drag limits motions, and in unlike airflow conditions. And we use like some studies from NASA and physics principles that you would see in aerodynamics, and like conservation of energy and all that. So over here you can just like see lift equals weight, because like they're like opposites of each other, and like that's like when it's like perfectly balanced, lift and weight would be the same, and thrust and drag would be the same. It's like perfectly balanced and in a stable position. So these are like some of the how you increase velocity due to lift. I couldn't really show the formula well over here because of just like I couldn't put the formula directly in a Google Docs, but um uh like it's a formula that like relates velocity and lift. And then so the next week we were like just seeing like what wing geometry would help. Like that's basically just like the airfoils are basically like the shape of the wing. So like if you look at a wing from the side, the main shape, that's an airfoil. Angle of attack is basically like how the main airstream hits the airfoil, and how like each type or like shape of airfoil gives a different amount of drag and lift. And like you can like change like the airfoil size and like the angle of like the way it's shaped. Like you can change its camber is basically how bended it is. Like you can make the airfoil bend a little bit to like better suit some angles of if certain angles of air and certain speeds of air, because like the speed of air also changes some of the factors of how well it performs in certain angles of attack. So if you're expecting to fly somewhere, or expecting to like operate mainly in a region with a certain type of wind conditions, and where like the wind is like most of the time going in one direction, then you can like customize an airfoil that will best suit it for that region or for that area. And then so we found out how like angle of attack and the camber and like all the other coefficients are related with like the shape of the airfoil. And then next we went into like the uh, actual in data interpretation. We got some data from NASA. NASA has like an airfoil uh as like an airfoil website where you can like make airfoil. You can get data from there and collect it. So I just like looked through them, and found some of the airfoils and like approximated them, got close to like the average and mean, and then we went into just like trying to put them in a graph and see at what conditions each airfoil is at its peak, and then like we just and then so it was like you see there's like a bunch of graphs that I have where it shows you what or I don't have them, but like I made them and then I put the results into this document where it tells me like which airfoils uh are- perform optimally in which conditions, which is like going back into like the optimal how well performance is based on like the wind conditions, climate conditions, pressure, or drag, not drag, like angle of attack and all of that. And then week 5 was just like calculating, like actual like data calculating with some formulas. So these are some numbers we got. We calculated air density, velocity, and wing area. There are formulas for these, but again, like I couldn't really put them in properly in Google Docs. So, and like they just look really weird and complicated, but they're like not that hard. But it just like looked weird in Google Docs, so I just like didn't put them in. But I will figure out a way to put the files in.